I'm going to talk about zeta regularization and values of the Riemann zeta function at negative integers.
Okay, where do we start?
So I think it begins with contemplating what we call infinite series. These would be getting numbers which you have to construct through some infinite process. So for example, kind of famous one is where you take a number which is like 0.99999 repeating. So the nines will keep on going forever. And you ask yourself, like, is this a number that I kind of already recognize? Is it equal to something else with a different name? And in this case, although from this perspective, the decimal expansion is very complicated, it's actually equal to 1. One way to try and convince yourself that this must be the value is if you take this thing here, let's call it like x. Let's say we don't know what it's equal to. But if I take this x and I multiply it by 10, well, we know multiplying by 10 just kind of shifts each decimal point like one thing to the right. So I'm going to get like 9.999 repeating. This thing looks a lot like the x, right? The x was like 0.999, 0.999. And so the only thing that's different about x and 10x is this 9 in front. So let's say I subtract the x from the 10x. Okay, so I get 10x minus x, and now I just get 9 because now everything else kind of cancels out here when I do subtraction. So here I'm getting 9x equals 9, and I've concluded, therefore, that x should be equal to 1.
I feel like I've been tricked when I see that. Like there's been sleight of hand, or there's something I missed.
I felt the same way, yeah, when I kind of first saw this. I mean, part of it is just you have to sort of decide, what do you really mean when you say equal? What do you mean by when you think about like infinite decimal expansions? And in math, there's a kind of formalism for this called convergence, and it's like if you have a number like this, where you kind of keep adding very, very small things to it, like 0.9 plus 0.09 plus, and so on, then if it's getting closer and closer to some target value, then we're just going to say it is equal to that target value. So there's a kind of framework of analysis here which we're kind of suppressing, which really justifies like why you're allowed to say these kinds of equalities.
But is that a bit lazy though? If I went to the Olympics and I was running towards the finish line, as I get closer and closer, I still haven't reached the finish line. I'm not going to get the gold medal until I cross it. Right. Just like 0.99999 isn't going to get its oneness until it crosses the finish line, and it doesn't cross the finish line.
So I think this concept of infinity is kind of a mathematical, maybe abstraction to some extent. Like in our daily lives, we rarely encounter a process which is truly infinite, where you can really just keep going forever. And so, so it's a bit of an abstraction that is introduced for kind of mathematical convenience, like it makes things work. This kind of thing is counterintuitive because in kind of real life, we don't necessarily encounter infinite processes. So I'm going to show you another example where you can apply similar reasoning, but it can lead you astray. So let's do something like 1 plus 10 plus 100 plus 1,000. And I think you see where I'm going. I'm just going to keep adding a number which gets one more 0 at the end. So now this is very much not converging. In the previous case, when we did this 0.999 thing, you kept adding something smaller and smaller, and you're getting closer and closer to the target value. Here, we're adding something bigger and bigger and bigger. So we're kind of not getting closer to anything.
It's blowing up.
Blowing up, exactly. However, you could try to carry out the same sort of reasoning to say, well, suppose this was a number x. Then what would 10x be? Well, you would get 10, right? 10 times 1 is 10, plus 10 times 10 is 100, plus 10 times 100 is 1,000, and so on. So it actually looks exactly the same as x, except that it's missing a 1. So you could try to say, well, therefore 10x is actually really just equal to x, except it's missing a 1. So let's call it x minus 1. And then we would manipulate it here, so I could move this x to the other side, so I'd get 9x is negative 1. And the conclusion would be that x is negative 1 over 9.
So that big blow up thing now.
Yeah,
right.
So this doesn't really look right? Because 1 is positive, 10 is positive, 100 is positive. You know when you add positive numbers to positive numbers, it's still positive. And in fact, it's getting more and more positive. It's getting larger and larger and larger in the positive direction. How could it end up being negative 1 over 9?
Well, what is the problem? You did the same thing last time and we were comfortable. What's different this time?
Right. So what's different this time is kind of, in the sense that I said last time, you're allowed to take this infinite expression and assign to it a value. And then you can perform this reasoning to figure out what the value is. So this is some value, the value turned out to be 1. In this case, this infinite sum doesn't actually have an official value. It's not allowed to have a value. So when you try to analyze what that value is, you're going to get gibberish because it's not true that this is equal to some number.
So the problem started the minute you said x equals.
Yeah. I said x equals this, and I was trying to work with x as if it's a number like any other number, but that's not really allowed. But there is something legit here. So I think that's part of math, is that sometimes you find something and it's not technically in the rule book that already exists. As part of the research process is to figure out like to what extent is it justified, or what maybe it's a shadow of something which is actually allowed.
I like that, a shadow of something that's allowed.
A lot of times, like people ask, like, what is math research about? And sometimes it's just kind of doodling where you do something and you say, well, this isn't really allowed, but it seems like it would be -1/9, and what is the meaning of that? So the meaning of that here falls under some topic which we call analytic continuation. And the idea will be, I can take an expression, let's try to kind of generalize these two things. So I'll take something like 1 plus r squared plus r cubed, and so on. This thing will have some value x if r is less than 1, an absolute value. So in this theory of infinite sums and convergence, this thing will be a number if this absolute value of r is less than 1.
Because it won't blow up.
Because it won't blow up, exactly. Because if r is less than 1, when you raise it to higher and higher powers, it'll shrink to 0. So you're adding very little at each stage, so it's going to kind of reach some target. And it turns out that this will be equal to 1/1 minus r. To see this, you can play the same games we did before. You can say, well, I'll take r times x, and that'll be r plus r squared plus r cubed plus so on. And that's the same as x, except that this 1, right, is present in x and it's not present in r times x. So what we see is that this is equal to x minus 1. And then if we kind of shift things around to the side divided by the r minus 1, we're going to get the conclusion that x is equal to 1/1 minus r. Okay, so what we just discussed was that I have this thing 1 plus r squared plus so on, an infinite sum, and it actually equals this kind of more finitary expression, 1/1 minus r, if the absolute value of r is less than 1. This left side, although I said it's not really a number if r is bigger than 1. It's not allowed to be assigned some specific value because it doesn't converge. The right side, you see this 1/1 minus r makes a lot of sense, even if r is something like 10 or 100, something bigger than 1. So the way we think about this is that these two sides, they're equal on some part of the number line, right? If r is like between -1 and 1, then these two numbers will be equal. Say r is in here. But then if r is bigger than 1, then only one of them makes sense. So this is this analytic continuation that I'm referring to, where we think of it as like, in order to make sense of this value, when a priori it's not allowed, like you're not allowed to take the sum when r is bigger than 1, you need to find some other way to express it. And that other way may then make sense, even when kind of the input r is not in the original domain of definition.
Okay.
That's this thing that we call analytic continuation. It's like you have a thing, and you need to find some other way another perspective on it which makes sense in a kind of broader context.
If you had a name, right, like your name's Tony.
Yes.
But if you had a name with an infinite number of letters, I couldn't write your name, so I don't know what to call you.
Right.
So someone says to me, all right, call him Tony, because that's got a finite number of letters and your brain can handle that.
Yeah.
That's all well and good, and it helps you and I communicate and for me to call to you from across the room. But it's still not your name. Like, I still haven't said your name. Mm-hmm. Isn't that the problem here? Like, we've assigned a value to this series, but it's still not the value.
So that's maybe a bit more philosophical, but I would say, going back to this example, 0.999, what do we mean when we say this is equal to 1? And you could say, like, so I think what you're saying in this analogy is like, well, this isn't really 1, because 1 is 1, and this is not 1, so it's something else. But what we're trying to do here is create a formalism where this kind of thing, 0.99999, instead of saying, oh, it's an infinite number, not an actual number, but like something close to a number, we want to think of it as an actual number. And I'm saying it really is equal to 1. So I think in the analogy it would be more like, maybe in one language my name would be Tony, in another language it might be like Tony, repeated infinitely. But we would recognize we're talking about the same thing. They happen to have different names. You could call them different things, but really they are the same.
Does every series that you can conceive of have a unique identity under analytic continuation, or could 2 or 3 different series identify themselves by, minus a half or something like that?
You could definitely arrive at the same value with two different kind of appearances. For example, this is one where I could say 1 is really 1.000, and the 0 repeats. And that's going to be the same as this. You can also have examples of these infinite series which just don't have any other name that we recognize. And one of them is like 3.14159. So I'm getting at pi here. So this is not, there's not a simple way to write this, as like 22/7. I mean, that's an approximation, but there's no such thing like that. So it's not necessarily the case that every series has some nice value that we already had some other name for.
There are some people watching this, some Numberphile viewers, that are thinking very much about the sum of the integers at the moment.
I know this looks like a bit of mathematical hocus pocus sort of thing, but actually, in truth, it's not. And I'll tell you why we know it's not.
That is where I want to go next. So there are certain kinds of sequences, sort of like this 1 plus 10 plus 100, and so on, but a little more complicated, which have some historical significance and also modern mathematical significance. So that's what I'm going to talk about next. So I just want to recap. We decided that this kind of thing, 1 plus 10 plus 100 plus 1,000 and so on, it's not really equal to a number, but we can say in quotes is equal to -1/9. And what we mean when we say this is that there's another way to think about this thing. Like here, it's kind of this thing when r is 10. We can think of that instead as 1/1 minus r. And that's what we mean when we say this kind of equality. So there is a function of r, and that function can be extended to a region where it has a different appearance, but it still makes sense and it still has nice properties. And then you can plug r into that and get a well-defined number. And so here we're saying this 1 plus 10 plus 100. That's really the specialization when r is 10 of the left side. And then this left side is equal to some other function, which makes sense even when r is something like 10, even though this equality was originally when r is less than 1. So I'm going to do another example in the spirit, but it's slightly different, and it shows another one of these dangers of doodling without any rules. So if we take this sum 1 minus 1 plus 1 minus 1 plus 1 minus 1, continuing with alternating signs, suppose that this thing were to have a value. What would its value be? So you could say, why don't I group up this sum like this? Break this into groups of 2. So 1 minus 1, and then I add 1 minus 1, and I add 1 minus 1, and so on. So here, this is, of course, 1 minus 1 is 0, 0, 0. So I'm adding 0 to itself a bunch of times. So it should be equal to 0, question mark. But if I look at it a slightly different way, suppose I just group these things differently. Start with this one, we do the subtraction of 1 and the addition of 1 in one step. So then I do 1 minus 1 plus 1. And then I subtract 1 and I add 1. And I keep doing this. So now I'm going to get 0. Here I'm also going to get 0. I've just gotten a different argument that it's 1 minus 0, blah, blah, blah. And that would be 1, because you're starting with 1, you're doing nothing to it. So it seems like we've given different arguments that this should have these two different values, 0, 1. What's going on here? So this is one of the dangers of kind of manipulating the infinite sums without any rules. So that's why in math we have rules about what's really allowed and what's not allowed. Sometimes we break those rules in order to try and guess what sort of things out there that we haven't discovered yet. But in the end, we need to justify things with rules. And here, both of these computations, they're not really justified because of this issue that this thing isn't converging. It's really like oscillating. It's like starts at 1, goes to 0, and then 1, and then 0, and so on. So the way to justify what the value really should be is to say, well, this thing here is, again, the specialization of this kind of expression when r is -1. So when r is -1, this 1 plus r squared and so on will be this expression here with alternating signs. And our recipe is telling us that we should think of it as 1/1 minus -1. So that's 1/2. So in fact, the correct way to regularize this kind of infinite sum, at least in this kind of context, is going to produce the answer of 1/2.
Which seems halfway between the two, you can.
Exactly, yeah. It's halfway between these two extremes.
Is that just a coincidence that it's halfway between the two extremes, or?
It would certainly have to be between these two extremes, but there's definitely no rule like, oh, it'll always be half of the. If you have two different answers, it'll be the average of them. There's no rule like that. Okay, so now I'm going to discuss a slightly more complicated example, which is related to things that mathematicians these days care a lot about, and it also has some historical significance. So I'm going to consider a sum that looks like this. 1 plus 2 plus 3 plus 4 plus, and so on. And this, like the other ones we've seen, is certainly not converging. You're adding numbers that increments are bigger and bigger, so they're not kind of converging to some specific target. Nevertheless, it's actually interesting to think about when we have this expression, if we were to assign to it some numeric value, what would that value be? And then at the end also, how can we justify it? How are we going to analyze this? So I'm going to do something which is mathematical doodling, where we're going to do some operations. We're going to not worry so much, at first at least, that we're breaking some rules, like assigning this numeric value. And then we're going to try and justify the conclusion later. If I look at this thing here, suppose I contemplate negative 4x. So I can calculate what this is, but I want to position it in a certain way. So I'm going to think of it as negative 4 times this 1, and then I have to add negative 4 times this 2, but I'm going to put that over here. So I'm sort of doing things in steps of 2 here, so minus 12 and so on. And the point of it writing it this way is that now if I add the x and the negative 4x, on one side I'm going to get, of course, negative 3x. But then the other side I'm going to get 1 minus 2 plus 3 minus 4, and so on. So it'll be the kind of alternating sign version of the original x. Now I'm going to do something kind of similar again, where I just say, well, negative 3x is, and now I'm going to shift the positioning by 1. So it's like 1 minus 2 plus 3 minus 4, and so on. So I'm writing the same expression, but just shifted over by 1. And the reason I did that is because then I'm going to add these things, and I'm going to get negative 6x, and it's going to be equal to this 1 minus 1 plus 1 minus 1, and so on.
Did you break any rules by doing that little shift, moving them over? That was just for visual reasons, wasn't it? That was just to help.
Yeah. The shifting, it shouldn't do anything, right? Because it's the same expression. I mean, the adding and subtract the positioning doesn't really matter. Of course, I broke rules when I wrote the equal sign, and I was treating x as a number. So this is all on kind of shaky grounds. But this is the kind of doodling which was done by a mathematician from the 1700s named Euler. And it turns out that it does produce the correct conclusion. So it's kind of interesting. But we have to, of course, in math, we have to go back and justify, like, why is it okay?
All right, so minus 6x gives us something we're familiar with. You showed us this earlier.
We saw that, yeah, exactly. We saw it earlier. We saw that this is 1/2, and so the conclusion is that x is actually negative 1 over 12.
Yeah. Sold. Except for that naughty thing at the start.
Right. So what does this kind of conclusion actually mean? How does it justify it, and sort of what is the significance of that? So earlier on, we were talking about this function 1 plus r squared plus r cubed and so on as a function of r. And then we said, wait, as a function of r, it's equal to 1 over 1 minus r, at least when r is less than 1 in absolute value. And then this 1 over 1 minus r, actually, that has fewer restrictions on what you can plug in for r. You can plug in any r that's not equal to 1. You'll get a sensible answer. So similarly here, there's this thing called the Riemann zeta function. So it's a function of a variable s, and it's 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s, and so on. So you're going to see every positive counting number here. So the way we would write this in shorthand is sum over all n of 1 over n to the s. We need to ask ourselves, like, where does this expression actually make sense? And it's only going to make sense when s is big enough, because you need to make sure that you're adding very, very small increments in order to get this quantity to kind of converge to a fixed value. So it turns out that this is okay if s is bigger than 1. Mathematicians care about this Riemann zeta function because its properties are actually closely intertwined with the distribution of prime numbers. So if you've heard of the Riemann hypothesis, one of the kind of longest outstanding conjectures in mathematics, then it's about the properties of this function.
Cool, so that's a big deal.
It's a big deal, yeah. So I said this makes sense if s is bigger than 1. So for example, there's kind of famously zeta of 2. You can plug in s equals 2, and here you're going to get pi squared over 6.
If s isn't bigger than 1, the problem is what your denominators become less than 1, and therefore the actual numbers become bigger, the integers become bigger, and just turns into this whopper again.
Exactly, yes. So when you have these infinite sums, in order for that to have a well-defined target value, then the increment that you're adding each time has to get small quickly enough. But actually, when s is less than 1, the increments are not small enough. And so, for example, if s is negative 1, then what you would see in this expression is something like zeta of -1. You tried to say it's equal to, I'm going to put this in quotes, because now you think it's a negative sign, so it's really 1 plus 2 plus 3 plus 4.
There it is.
So on. This expression that we saw before that we said should be equal to -112.
Cool.
It's a similar story to here where this zeta of s, I've defined it in a way that sort of only makes sense when s is bigger than 1, but you can produce some other description of it which makes sense actually when s is less than 1 as well. As long as s is not equal to 1, then it will have a well-defined target number. Say zeta of s makes sense as long as s is not equal to 1. This makes sense means there's some analytic continuation of it, so there's some other perspective on this definition that you're allowed to plug in, for example, -1 and 2. And it is true that zeta of -1 is -112.
Is that arriving at -112 using a significantly different technique? Like, is it quite the doodling technique you showed me, which you said was on slightly shaky ground? Is the technique that you would use this second way different? Is it?
I think the doodling, you can make it legit. There's different ways to approach this, but the doodling can be turned into a real proof. But there's certain doodlings which I didn't show, which could lead you to the wrong conclusions. You have to be careful of those. Those cannot be. So it's a bit of a fine line at the end. You definitely have to do more work to justify it. But basically, the doodling is part of maybe like it's the tip of the iceberg on some actual mathematically rigorous approach.
So if someone tells you that the sum of all the positive integers, all of them to infinity, whatever that means, is minus a 12th, what do you say? What do you say to them? Do you say, yeah, I'm cool with that?
Well, my first instinct would be like, what are you talking about? That's obviously ridiculous. But I guess after studying the theory, then then you sort of think like, oh, I know what you really mean. But I'll just say it's kind of a funny anecdote, which I think is somewhat convincing, is that sometimes you're doing some actual calculation, like in physics. There's this thing called the Casimir effect in quantum mechanics, and you're trying to predict some experimental outcome, and you're trying to calculate the energy, and you run into this kind of thing. You say like, oh, seems like the physics is telling me the energy is something like 1 plus 2 plus 3 plus 4 and so on. And so of course that doesn't make sense. But then you say, okay, so maybe the correct way to make sense of it is in the sense of the zeta function. This is called zeta regularization, where it's a kind of procedure by which when I see certain types of infinities that look like this kind of thing, I'm going to replace them by the value of the zeta function. And it turns out that this this leads to a kind of an experimentally verifiable outcome. So you could have the point of view that like when you see these kinds of infinities, it's nature's way of really telling you that it should be this other kind of -112 thing.
Okay.
I just wanted to give a little bit of extra context and information about today's video, because as you may be aware, we've covered the issue of -1/12 before, pretty much exactly 10 years ago. Now, when I was in Berkeley and met up with Tony, who was in today's video, I didn't know what he wanted to talk about, and he hadn't watched all the Numberphile videos. He didn't know we'd covered a -12 before. When I realized what he was going to be talking about, I thought it might be an interesting experiment to hear someone else explain the whole concept, and Tony was cool with that. So he hadn't seen the previous video, and I thought it might be interesting for you to watch this and compare it with what's been said before. Now, going back to the original video 10 years ago, one of the people in that video, also called Tony, was Tony Padilla, and he's been interested in a -12 ever since. It's followed him around. And recently, him and a collaborator have written a new paper all about it, about how it links in with physics, how -12 could be a shield nature uses to protect us from infinity. If you'd like to hear more about that, I've uploaded that video newly to Numberphile as well. I'll include a link in the description, and I'll also include a link to a playlist to all our -12 videos. Knock yourselves out.
It's because of that sharp transition. He says, you don't have to do it like that. There are other ways to regulate this sum. Now, I'm not doing anything weird, no weird analytic continuation, anything like that. Terence Tao says there are other ways to regulate sum. Don't do the sharp transition, do a smoother one. Something that takes you between 1 and 0 in a much smoother way.
It's blowing up, you get larger and larger, so there is no sense of getting closer to anything.
So traditionally, what do we do with the divergent series? We just ignore them?
We just ignore them, we just throw them away. But the question is whether this is the right approach, whether there is actually something we can say about such a series